How are industrial pipe flanges built to meet the extreme demands of pipelines worldwide? This video takes us through the full journey, showing every step from raw billet to finished product, revealing both scale and technique. The process stands as proof of the balance between force and accuracy. First comes billet preparation. Solid steel bars are cut into sections according to the intended flange size. They are heated in furnaces until glowing hot, ready for forming. Each billet holds potential energy that will be unlocked during forging. Next is forging and rolling. Giant hammers compress the grain structure, while ring rolling machines shape the steel into a circular profile. The transformation during this phase is striking. Afterward, controlled cooling maintains toughness and reduces internal stress. This stage ensures reliability for use in high-pressure systems. Machining follows. Lathes refine the diameter, while drilling machines create perfectly aligned bolt holes. Even a fraction of misalignment could cause leakage in operation. Automated tools provide consistent results across large production batches. The speed of these machines is remarkable. Finally comes surface treatment and inspection. Anti-corrosion coatings extend surface life, and rigorous checks verify quality. Stacks of finished flanges highlight global demand. These components then leave the facility, ready for service in energy, construction, and infrastructure projects. Every slab of steel, nickel, and titanium must face furnaces and mills before becoming coils and plates for global use. The hot rolling facility at ATI reveals the journey, combining extreme heat, enormous forces, and advanced control systems. The scale of engineering here leaves a strong impression on anyone following the process. The sequence begins with large ingots transformed into slabs. Different furnace types, walking beam, soaking pit, induction, and car bottom are used to heat these materials uniformly. The goal is to reach temperatures where deformation is possible without damaging the internal structure. Each furnace stage is like a gateway, unlocking the next transformation. Once hot, slabs enter the roughing stands. Edgers and roughers reduce thickness and shape the material for subsequent passes. With roll forces reaching up to 60,000 kilonewtons, the equipment pushes the limits of mechanical power. Every pass under the rollers demonstrates sheer industrial strength. The slabs move to finishing mills equipped with smart crown technology, hydraulic gauge control, and roll shifting. These systems ensure consistent thickness, flatness, and surface quality. The precision of alignment here is essential for demanding applications such as pipelines and automotive components. Work roll lubrication and quick roll change tractors support continuous operation. The ability to swap rolls within minutes shows remarkable efficiency. Cooling follows, with laminar and turbo-laminar systems regulating temperature drop. This step is vital for controlling grain structure and mechanical properties. Power coilers then wind the product into large coils, ready for further processing. Seeing the glowing strip form into a tight coil is both technical and striking. Final steps include transport to inspection, weighing, strapping, plasma cutting, and sampling. Heavy gauge coils are checked with specialized cutters before delivery. Stacks of finished coils underline the immense production capability of the mill. These products, ranging from carbon steel to titanium alloys, move on to serve energy, automotive, appliance, and construction sectors worldwide. Turning gears of extraordinary size demands equipment built for power and adaptability. At Horsberg and Scott, vertical turning machines handle diameters ranging from 20 to 50 feet. The process begins with mounting the gear blank onto the massive table. Columns can be adjusted to expand working range, allowing even 40-foot components to rotate securely. Seeing such heavy steel move so smoothly is impressive. Live spindles then perform drilling, tapping, and milling while the gear remains fixed. Combining multiple steps in one setup boosts efficiency. Another machine, a 2-meter vertical turning center, includes pallet changers for quick transitions. Continuous machining without downtime shows remarkable capability. The integration of strength and flexibility defines this facility. Final operations ensure bolt circles and surfaces meet exact standards. Steel bars are heated in a furnace, reaching the ideal forming temperature. They move along a conveyor into the skew-rolling machine, where rotating dies shape each bar into a perfect sphere. The rhythm of glowing steel transforming so smoothly feels powerful. Finally, balls roll out in sequence, ready for grinding applications in heavy industries. Standex applies laser hardening directly on gear teeth, strengthening only the contact zones. This targeted process prevents warpage and extends service life. The glow of the beam against steel feels strikingly intense. Blades that cut through wood and steel eventually lose their edge, and restoring them to peak condition is essential. The rhythm of the machine creates a hypnotic sense of progress as each tooth is attended to. This automated bandsaw blade sharpener shows how technology renews every tooth for reliable performance. The first sight of the machine draws attention instantly, promising sparks and motion. The sharpening of a bandsaw blade begins with an automated feeding system, drawing the long steel loop into position. Each tooth is aligned with exact spacing before grinding begins, ensuring every edge is evenly presented to the wheel. Operators monitor the process closely, noting subtle differences in tooth shape and wear. Next, the grinding wheel engages the first set of teeth, removing worn material and restoring a uniform profile. Sparks mark the point of contact as steel meets abrasive, giving the blade renewed sharpness. The smell of heated steel hints at the power involved in reshaping metal. As the process continues, the automation indexes the blade forward tooth by tooth. A consistent cycle of grinding, indexing, and advancing repeats, producing accuracy across the entire loop. Small adjustments in wheel pressure ensure the finish is flawless across varying tooth angles. The smooth advance of the steel feels almost alive as it circles through the system. Once the full rotation is complete, the blade has regained its sharpness, ready for high-performance cutting once again. Some machines allow for multiple passes, depending on the wear condition of the teeth. Automated systems like this increase productivity by reducing downtime and maintaining consistent blade quality. The blend of sparks, motion, and sound delivers a sense of unstoppable efficiency. A new chapter in aircraft manufacturing unfolds with the creation of the multifunctional fuselage demonstrator, the largest thermoplastic structure of its kind. This project highlights not only lightweight strength but also advanced joining technologies. The scale of innovation feels both daring and impressive. The process starts with the skin, built layer by layer using in-situ consolidation. Tape is laid across the mold, adding up to 53 kilometers in total, forming the continuous outer surface. Each layer gives a sense of growth, like the shell of an aircraft coming alive. Next, 44 Z-shaped stringers are produced by compression molding. They are prefixed onto the skin through robotic ultrasonic spot welding, with every 500 millimeters receiving a weld. The sonotrode delivers high-frequency vibrations, heating the bond line exactly where needed. After prefixation, continuous ultrasonic welding secures each stringer along its full length. A camera-based correction system keeps the end effector on track at travel speeds reaching 5 meters per minute. The pace is fast, yet the result looks remarkably stable. Frames are then introduced, 24 C-shaped parts manufactured by compression molding. Using a weld bridge, these frames are aligned with the skin and attached through resistance welding. Pneumatic modules close around the flanges, and current runs through carbon-based elements to make the joints. The combination of pressure and electricity feels like raw engineering power at work. Once the frames are fixed, cleats are integrated. A cobot extracts each cleat from a magazine, aligns it by touching the skin, stringer, and frame, then welds it into place. Around 158 cleats, resulting in 316 welds, are added to complete the assembly. In the end, the upper shell of the fuselage emerges as a thermoplastic milestone, lighter, stronger, and built with methods pointing toward aviation's future. The finished form carries the promise of efficiency in every flight. Across industries where power and reliability matter most, large-scale gears are the silent core of operations. Their size, accuracy, and durability define how cement and mineral plants continue running at full strength. The process begins long before any metal is cut. Projects are initiated with detailed planning and engineering, calculating gear geometries to the highest standards. This early stage builds confidence, knowing every gear is designed for decades of heavy use. Raw materials then undergo stringent testing before entering the workshop. Specialized gear shapers, some with upgraded CNC control systems, bring flexibility to manufacture complex profiles. Hoppers are used to cut both internal and external toothing, ensuring capability across a wide range of gear types. Even the oldest machines, maintained with care, still produce results that match modern expectations. Spiral bevel gears are produced on large-format machines, able to handle workpieces up to 2 meters in diameter and pinion shafts of equal length. Additional milling systems cover other geometries, allowing shafts and wheels up to 2.5 meters in size. Soft cutting comes next, performed before heat treatment. Within in-house facilities, parts are hardened, tempered, quenched, or nitrated to strengthen structure and extend lifespan. Hardness testing ensures metallurgical integrity for heavy-duty service. This transformation in strength is a moment where raw steel begins its journey toward endurance. Once treated, components are ready for hard cutting by CNC-controlled machines, shaping precise bevel gears with smooth surfaces. Milling centers finalize forms with software-guided accuracy. Quality inspection follows, supported by climate-controlled measuring rooms and specialized Klingelnberg equipment. These inspections reflect the uncompromising standards applied at every stage. Turning, grinding, and girth gear manufacturing expand production capacity further, supporting extremely large parts. Assembly combines human expertise with advanced tools, uniting elements into complete gear units. The cooperation between skilled workers and machines gives the final product a unique character. Before delivery, gearboxes undergo extensive testing and oversized transport arrangements. For over a century, these drive systems have powered industries with strength built to last. Large steel plates take on a powerful transformation when turned into dished heads, the rounded components essential for tanks and pressure vessels. Watching the process unfold reveals both strength and control in metalworking. The first step is cutting the raw material to exact dimensions. Large steel sheets are measured, marked, and trimmed before edges are welded together to form a circular blank. Once the blank is secure, the workpiece moves forward for shaping. Pressing comes next, where a hydraulic press applies immense force onto the steel plate. Slowly, the flat sheet begins to curve, forming the initial bowl shape. This moment shows how controlled pressure can redefine the nature of solid steel. The press ensures uniform curvature, preparing the material for its next stage. Flanging is then performed to shape the edge of the dish. The rim is bent outward, giving the component its final geometry to fit with adjoining structures. It is at this stage that the steel disc truly becomes a functional dished head. Throughout the process, emphasis is placed on durability and accuracy, ensuring the component meets strict standards. With these steps complete, the dished head stands ready for heavy-duty applications in tanks and industrial vessels. Inside the halls of renewable energy, giant rotor blades begin their journey. Apprentices shape them from composites, showing how hand skill and technology blend in production. Work starts with layering fiberglass and carbon fiber sheets. These materials are then infused with resin, forming strong, lightweight structures. The scale of each blade is striking, stretching over 50 meters. Next comes curing in large molds, where heat and pressure bond the parts together. Grinding and sanding follow, refining every surface. Each step reveals how demanding such manufacturing truly is. Finally, blades are coated, inspected, and matched for balanced weight before being sent for assembly on towering wind turbines. Strong assemblies are born when steel pieces are fused with modern welding techniques. At Bruck, Welding integrates forged and rolled parts into complete assemblies. The process offers a wide range of techniques: manual and semi-automated MIG, MAG, TIG, as well as submerged arc welding. It is impressive to see how such variety ensures flexibility for different projects. Heavy turntables support loads up to 30 tons, enabling TIG hot wire and rotating head systems to refine surfaces. Every weld adds durability, enhancing resistance to wear and corrosion.